This is Sleepy Space, a slow space story to help you fall asleep. There is something wrong with the universe we live in. On a clear night, far from city lights, the stars appear calm and orderly. Fixed points of light scattered across a quiet sky. From the ground, everything seems stable, predictable. But when astronomers step back, far beyond what the human eye can see, a different picture emerges. On the largest scales, the universe is not random. Galaxies trace enormous filaments stretching across billions of light years. Vast clusters form where these filaments intersect, and between them lie immense regions where almost nothing exists at all. This structure, known as the cosmic web, is one of the great successes of modern cosmology. It aligns with our equations. It emerges naturally from our simulations. By every reasonable measure, it is exactly what the universe should look like. Almost. Because when scientists study the oldest light in existence, the faint afterglow left behind when the universe was less than 1 million years old, they find something that does not belong. This ancient radiation fills the entire sky. It arrives from every direction with extraordinary uniformity, carrying a nearly identical temperature wherever we look. A signal of remarkable balance in the early universe, except in one place. In a region of the southern sky, this ancient light is slightly colder than it should be. The difference is small but persistent, measured again and again, refusing to fade away. This region spans an area roughly 20 times the width of the full moon. In physical terms, it corresponds to a structure nearly 2 billion light-years across, far larger than anything that should form so early in cosmic history. According to our best models, it should not exist. Over the years, scientists have offered explanations. Some invoke exotic physics from the universe's earliest moments. Others argue it may be nothing more than a rare statistical coincidence. An unlikely fluctuation in a universe large enough to allow them. But there is another possibility, one that is simpler in principle and far more unsettling in implication. What if the anomaly is not distant at all? What if the reason this cold region exists is because of where we are? What if everything we can observe, every galaxy, every cluster, every edge of the visible universe, lies inside an enormous region of emptier than average space? A cosmic void so vast that it subtly alters how light reaches us. So large that it affects how we measure the expansion of the universe itself. This is not science fiction. It is a genuine hypothesis explored by cosmologists, and it directly challenges one of the most important assumptions we make about the universe, that our location is ordinary. For centuries, science has steadily removed us from the center of things. Earth is not the center of the solar system. The sun is not the center of the galaxy. The galaxy is not the center of the universe. We are meant to be unremarkable observers in an otherwise uniform cosmos. But if we reside inside a vast cosmic void, that assumption breaks. It would mean that some of our most trusted measurements, distances, expansion rates, even the inferred age of the universe, may be subtly distorted by our surroundings. It could explain why certain observations refuse to agree with one another. The problem is that we cannot step outside our cosmic neighborhood to verify it. Every observation we make comes from within the universe we are trying to understand. If our location is unusual, detecting that fact becomes extraordinarily difficult. Yet astronomers are not without clues. They can map the distribution of galaxies around us. They can study how light cools and bends as it travels through space. And they have found hints, faint, incomplete, but persistent, that our region may be less dense than the cosmic average. Whether those hints point to a vast void or to coincidence remains one of the most quietly troubling questions in modern cosmology. To understand why scientists would even consider such a possibility, we first need to examine how we measure the universe itself and how fragile those measurements may be. The universe, when viewed from far enough away, resembles a sponge. Not in substance, of course, but in structure. There are dense regions where matter clusters together. There are tendrils connecting these clusters, and there are empty pockets scattered throughout. This is the cosmic web, the largest pattern of organization we know of in nature. Imagine zooming out from Earth, past the Moon, past the planets, beyond our solar system. You would first see our galaxy, the Milky Way, a spiral of several 100 billion stars. Continue outward, and you would notice we are not alone. Other galaxies surround us. Some are close enough that gravity binds us together into what astronomers call the local group. Keep going, and you would see that galaxy groups themselves cluster together into even larger structures. These clusters of galaxies gather along vast filaments. The filaments stretch across space like threads in a cosmic tapestry, connecting one dense region to another. Some of these threads span hundreds of millions of light years. Along their length, galaxies are strung like beads, drawn together by gravity over billions of years. Where filaments intersect, you find the densest regions of all, superclusters, collections of galaxy clusters containing thousands or even tens of thousands of individual galaxies. But between these bright filaments and clusters, there is mostly darkness. These are the voids, regions where galaxies are scarce, where matter is spread thin, where the density of everything we can measure drops well below the cosmic average. The voids are not small. A typical void might span 30 to 50 million light-years across. Larger ones can reach 300 million light-years or more. To put that in perspective, the distance from our galaxy to the Andromeda Galaxy, our nearest large galactic neighbor, is only about 2.5 million light-years. A large void could contain more than 100 such distances. These voids are not truly empty. If you were somehow placed in the middle of one, you would still find galaxies. They would just be fewer and farther between. The density of matter in a void might be 10 or 20% of the average density of the universe, sometimes even less. The galaxies that do exist in voids tend to be smaller, dimmer, and less active than those in the dense regions. They formed from smaller initial concentrations of matter, and they have had fewer interactions with other galaxies over cosmic time. The cosmic web forms through a process that is elegant in its simplicity. In the early universe, matter was distributed almost uniformly. Almost, but not quite. There were tiny variations in density, regions that had just slightly more matter than their surroundings. These slight overdensities had slightly stronger gravitational pull. Over time, they attracted more matter from nearby regions. The rich got richer. The dense regions grew denser, and the places they drew matter from became less dense, emptier. These growing empty regions evolved into the voids we see today. This process has been running for more than 13 billion years. The cosmic web is the cumulative result of gravity acting on those initial tiny variations across the entire history of the universe. Simulations confirm this picture. When scientists model the evolution of matter in an expanding universe, starting from nearly uniform conditions with small random variations, they consistently produce structures that look remarkably like what we observe. Filaments, clusters, and voids emerge naturally from the mathematics. For most of the 20th century, cosmologists operated under an assumption known as the Copernican principle. Named after Nicholas Copernicus, who demonstrated that Earth is not the center of the solar system, this principle states that we do not occupy a special or privileged position in the universe. Our location should be typical, average. When we look out and measure the properties of the cosmos, we should be seeing what any observer anywhere in the universe would see. This principle has served us well. It allows us to take observations from our single location and extrapolate them to make statements about the universe as a whole. It underlies much of modern cosmology. When we say the universe is expanding at a certain rate, we are implicitly assuming that this rate is the same everywhere, not just here. When we describe the density and composition of the universe, we are assuming these values represent cosmic averages, not local peculiarities. The cosmic web supports this view, at least on large enough scales. Yes, there is structure. Yes, there are dense regions and empty regions. But if you average over large enough volumes, the universe looks roughly the same in every direction. This is called isotropy. And if you were to observe from any other location in the universe and average over similarly large volumes, you would see the same patterns. This is called homogeneity. Together, these properties form the foundation of the cosmological principle, the idea that the universe is fundamentally the same everywhere. Surveys of galaxy positions confirm this, at least to a point. When astronomers map the locations of millions of galaxies and analyze the patterns, they find that the statistical properties of the cosmic web are consistent across vast distances. The size distribution of voids appears to be the same whether you look in one direction or another. The density of matter, when averaged over large enough regions, comes out to similar values regardless of which part of the universe you examine. But there is a catch. All of these observations are made from here, from our particular location in space. We assume this location is typical because the principle says it should be. We have no way to verify this assumption directly. We cannot send a probe to another part of the universe and confirm that things look the same from there. We can only observe from where we are and infer that our view is representative. What if our most fundamental assumption about our cosmic address is wrong? What if we do occupy somewhere special after all? In the early universe, roughly 380,000 years after the Big Bang, something remarkable happened. The universe had been expanding and cooling since its birth, and it finally reached a temperature at which atoms could form and remain stable. Before this moment, the universe was too hot. Any atoms that tried to form were immediately torn apart by energetic radiation. Matter and light were locked together in a dense fog. Photons could not travel far before colliding with charged particles. But when neutral atoms formed, the photons were suddenly free. Light decoupled from matter and began streaming through space. That light has been traveling ever since. As the universe expanded, the light stretched along with space itself, shifting from visible wavelengths to microwaves. Today, we detect this ancient radiation coming from every direction. We call it the cosmic microwave background, or CMB. It is, in a very real sense, a baby picture of the universe. When astronomers first detected the CMB in the 1960s, they found it to be remarkably uniform. No matter where they pointed their instruments, the temperature was the same to within a fraction of a degree. This uniformity told them that the early universe was almost perfectly smooth. Almost, but not quite. Later, more sensitive instruments revealed tiny variations in temperature. These variations were incredibly small, just a few parts in 100,000. But they were there, and they were crucial. These temperature fluctuations corresponded to density variations in the early universe. Slightly warmer regions had slightly less matter. Slightly cooler regions had slightly more. These were the seeds that would eventually grow into the cosmic web. The dense regions would attract more matter and become galaxy clusters. The underdense regions would lose matter and become voids. The pattern we see in the CMB today is a snapshot of the initial conditions from which all cosmic structure emerged. Scientists have mapped the CMB with extraordinary precision. They have measured the temperature across the entire sky to exquisite detail. And what they have found is that the variations follow a predictable pattern. There is a characteristic size scale to the fluctuations determined by the physics of the early universe. Most of the hot and cold spots in the CMB match this expected pattern beautifully, but not all of them. In the southern celestial hemisphere, there is an anomaly, a region where the temperature is significantly colder than the surrounding area. This cold spot is not small. It spans roughly 10 degrees across the sky, about the width of 20 full moons placed side by side. In terms of the actual early universe it represents, we are looking at a region approximately 1.8 billion light-years in diameter. The temperature deficit is measurable but not dramatic. The cold spot is about 70 millionths of a degree colder than the average CMB temperature. That might not sound like much, but in the context of the CMB, it is significant. The typical temperature variations in the CMB are only about 18 millionths of a degree. The cold spot stands out. It is colder than standard cosmological models predict should occur by chance. When this feature was first identified in data from the Wilkinson Microwave Anisotropy Probe in the early 2000s, scientists wondered if it might be a measurement error. Perhaps there was something wrong with the instrument. Perhaps there was some source of contamination in that part of the sky affecting the readings. But subsequent observations from other instruments, including the Planck satellite which mapped the CMB with even greater precision, confirmed that the cold spot is real. It is genuinely there in the ancient light of the universe. The question became, what could cause such a feature? In the standard model of cosmology, temperature variations in the CMB arise from density fluctuations in the early universe. These fluctuations are essentially random, the result of quantum processes stretched to cosmic scales during a brief period of rapid expansion called inflation. The amplitude and pattern of these fluctuations are well understood and well modeled. When scientists run simulations of how these fluctuations should appear in the CMB, they can predict the statistical properties of what we should see. The cold spot is unusual within this framework. It is not impossible. Random fluctuations do produce occasional features that deviate from the average, but the cold spot is rare enough that it raises questions. If you run many simulations of the CMB using our standard cosmological model, generating thousands of different random realizations of what the early universe could have looked like, a feature as cold and as large as the observed cold spot appears in only a small percentage of them. Perhaps 1 or 2%, maybe less, depending on exactly how you measure its properties. This low probability does not mean the cold spot proves our models are wrong. After all, if something has a 1% chance of occurring, and you observe many things, eventually you will see that 1% event. The universe is large. The CMB contains many regions. Finding one unusual feature is not necessarily grounds for overthrowing our theories, but it is enough to make scientists look more carefully, enough to ask whether there might be something else going on. One possibility is that the cold spot is exactly what it appears to be, a rare but perfectly normal fluctuation from the early universe, just a statistical outlier, bad luck or good luck, depending on your perspective. It might teach us nothing beyond the fact that rare events do indeed occur. Another possibility is that there is some exotic physics involved, perhaps a topological defect from the early universe, perhaps evidence of processes that occurred before or during inflation that we do not yet fully understand. But there is a third possibility, one that connects the cold spot not to the early universe itself, but to what lies between that ancient time and us. This strange cold patch in the ancient light of the universe led some scientists to ask an audacious question. What if the cold spot is not telling us about the early universe at all? What if it is telling us about where we are now? Light from the CMB has been traveling toward us for more than 13 billion years. During that journey, it has passed through all of the structure that has formed since the early universe. It has traversed regions where galaxies cluster densely together. It has crossed vast voids where matter is sparse. And as it travels through these regions, the light is affected in subtle ways. There is a phenomenon in cosmology known as the integrated Sachs-Wolf effect. It describes what happens to photons as they travel through regions where the gravitational potential is changing over time. In a universe that is not expanding or expanding at a constant rate, a photon that falls into a gravitational well and then climbs back out would experience no net change in energy. The energy it gains falling in would be exactly balanced by the energy it loses climbing out. But in our universe, which is not only expanding but accelerating in its expansion, this balance does not hold perfectly. Consider a photon traveling through a large void. As it enters the void, it climbs out of the gravitational potential of the denser regions surrounding the void. This costs energy. The photon becomes slightly red-shifted, slightly lower in frequency. As the photon travels through the void, the universe continues to expand. The void grows larger. Its gravitational potential becomes even shallower. By the time the photon exits the void and begins falling back into the denser regions beyond, the gravitational landscape has changed. The photon does not quite recover all the energy it lost on the way in. It emerges slightly more red-shifted than it would have in a non-expanding universe. This effect is subtle. For typical cosmic structures, the temperature changes it produces in the CMB are small. But for very large voids, the effect becomes more pronounced. A photon crossing a void that spans 1 billion light-years or more would lose a measurable amount of energy. When we observe that photon today as part of the CMB, we would measure it as being colder than average. This led some cosmologists to propose a provocative idea. What if the cold spot in the CMB is caused by an enormous void lying between us and the surface of last scattering, the distant shell from which the CMB photons originated? Not just a typical void, but a supervoid. A region of space so vast and so underdense that photons passing through it experience a significant integrated Sachs-Wolf effect. For this explanation to work, the void would need to be exceptionally large. Estimates suggest it would need to span somewhere between 1 and 2 billion light-years across. It would need to be significantly underdense, perhaps containing only 10 to 20% of the average matter density of the universe. And crucially, we would need to be located somewhere inside it, or at least very close to it, because the cold spot appears in a specific direction on the sky. If the void were far away in some other direction, it would not align with the observed feature. This hypothesis immediately raises eyebrows. It suggests that we occupy a special location in the universe, not just inside any void, but inside an extraordinarily large one. This seems to violate the Copernican principle, the assumption that our position is typical. The probability of randomly being located in such a rare structure is low. Most of the volume of the universe is not inside supervoids. Most observers, if they exist elsewhere in the cosmos, would not find themselves in such a location. Yet the hypothesis has a certain appeal. It provides a concrete physical mechanism for producing the cold spot. It does not require exotic physics from the early universe. It does not rely on being a 1 in 100 statistical fluke in the primordial fluctuations. Instead, it connects the observation to the large-scale structure that surrounds us. It turns the cold spot from a puzzle about the distant past into a puzzle about where we are right now. The supervoid hypothesis also makes predictions. If we are inside such a large, underdense region, we should be able to detect it through other means. We should see evidence in the distribution of galaxies around us. The density of galaxies in our cosmic neighborhood should be measurably lower than average. We should observe patterns in how galaxies move. Objects on the near side of the void would be flowing outward, away from the underdense center. Objects on the far side would show similar patterns. These are effects that, in principle, we could measure. Moreover, being inside a large void might affect other observations. It could influence how we measure the expansion rate of the universe. Light traveling through underdense regions experiences less gravitational influence than light traveling through dense regions. This could, in subtle ways, change the apparent brightness of distant objects. It could affect how we calibrate our cosmic distance ladder. It might even help explain other puzzles that have emerged in cosmology in recent years. Of course, the hypothesis faces challenges. Creating a void of the required size through standard gravitational processes is difficult. It requires specific initial conditions. It requires time for matter to flow out of the underdense region and gather elsewhere. Scientists have debated whether the universe is old enough for such a structure to have formed. They have questioned whether a void of this scale could remain stable, or whether it would have dispersed by now due to the overall expansion of space. If this hypothesis holds any truth, we need to understand how such an immense cosmic bubble could have formed in the first place. The formation of cosmic voids is written into the fabric of how the universe evolves. It is not a separate process that requires special explanation. It is simply the other side of structure formation. Where matter clusters together, it must flow from somewhere. The voids are the places it flows from. In the beginning, or at least in the earliest moments we can meaningfully describe, the universe was extraordinarily uniform. The density of matter varied from place to place by only a few parts in 100,000. These tiny variations were imprinted during inflation, that brief period of exponential expansion that stretched quantum fluctuations to cosmic scales. When inflation ended and the universe settled into a more sedate expansion, these density variations remained frozen into the fabric of space. Gravity began to act on these variations immediately. In regions where the density was even slightly higher than average, gravity was slightly stronger. These regions began to attract matter from their surroundings. The attraction was weak at first. The universe was still very dense overall, and the differences between overdense and underdense regions were minimal. But gravity is patient. It works slowly but relentlessly over cosmic time. As matter flowed toward the overdense regions, the underdense regions became even less dense. This created a feedback loop. The more matter that gathered in one place, the stronger its gravitational pull became. The more matter that left another place, the weaker its gravitational influence became. Over millions and then billions of years, this process amplified the initial tiny variations into the dramatic structures we see today. The first voids began to form surprisingly early in cosmic history. By the time the universe was 1 billion years old, underdense regions had already started to develop. They were smaller then, and not as empty as today's voids, but the basic pattern was already emerging. As galaxies formed in the overdense regions, the contrast between full and empty space became more pronounced. The evolution of a void follows a predictable trajectory. It starts as a region that is perhaps 5 or 10% less dense than average. Matter begins to flow outward toward the denser regions at its edges. As it does, the void grows. Not because it is actively pushing matter away, but because the matter that was there is being pulled elsewhere by stronger gravitational fields. The expansion of the universe aids this process. As space stretches, the already low density in the void becomes even lower. A typical void today might have evolved from an underdense region that was only a few million light-years across in the early universe. Over billions of years, it expanded to its current size of perhaps 50 or 100 million light-years. The matter density inside dropped to a fraction of the cosmic average. Galaxies that formed within the void found themselves in an unusual environment, relatively isolated from the gravitational influences that shape galaxies in denser regions. The size of voids is limited by several factors. The initial underdense regions from which they form were created by processes in the very early universe, and these processes had characteristic scales. The largest initial underdensities were only so large. There is also the matter of time. It takes time for matter to flow out of a region. The universe has been expanding for nearly 14 billion years, but that is not infinite time. Voids can only grow so large in that span. There is also competition for matter. Voids do not exist in isolation. They are surrounded by other structures, by filaments and clusters that exert their own gravitational influence. Matter flowing out of one void might encounter the gravitational pull of a nearby cluster, preventing the void from expanding further in that direction. The cosmic web represents a balance between all of these gravitational forces acting simultaneously across vast scales. When scientists run simulations of structure formation, they find that the distribution of void sizes follows a predictable pattern. Small voids are common. Modest voids are less common, but still numerous. Very large voids are rare. The probability of finding a void of a given size drops rapidly as the size increases. A void of 50 million light-years across might be fairly typical. A void of 200 million light-years across would be unusual, but not shocking. But a void of 1 billion light-years across? That enters the realm of the exceptional. The question is whether the known physics of structure formation can produce such a large void. Can gravity, acting on initial density variations over the age of the universe, create an underdense region that spans more than 1 billion light-years? The mathematics suggest it is difficult. Such a void would require a very large initial underdensity in the early universe. It would need favorable conditions surrounding it, allowing it to expand without interference. And it would need enough time for matter to migrate out of such an enormous volume. Some simulations do produce voids of this scale, but they are rare outcomes. They appear in perhaps 1 in 100 or 1 in 1,000 simulated universes, depending on the exact parameters used. This raises a question about fine-tuning. If we are inside such a void, are we simply lucky to observe a rare configuration? Or is there something about the initial conditions of the universe that makes large voids more common than we think? There is also the question of stability. A void does not remain static. It continues to evolve as the universe expands and as matter redistributes itself. Very large voids might be subject to instabilities. They might fragment into smaller voids or be disrupted by the gravitational influence of surrounding structures. Whether a supervoid could remain coherent over billions of years is not entirely clear. The physics of void formation is well understood, but scaling it up to encompass our entire observable region requires reconsidering what we know about cosmic expansion. In recent years, cosmologists have encountered a puzzle that refuses to resolve itself. Different methods for measuring how fast the universe is expanding give different answers. The discrepancy is not large, but it is persistent, and it is troubling. Both measurements appear to be correct. Both groups of scientists have checked and rechecked their work, yet the numbers do not agree. This disagreement has become known as the Hubble tension. It is named after Edwin Hubble, the astronomer who first demonstrated that the universe is expanding. The tension refers to the conflict between two different approaches to measuring the expansion rate, a quantity called the Hubble constant. One approach uses observations of the local universe. Astronomers measure the distances and velocities of relatively nearby galaxies, objects within a few 100 million light-years of us. They use what is called the cosmic distance ladder, a series of techniques that build upon one another to measure ever greater distances. The method relies on certain types of stars and supernovae whose intrinsic brightness is known. By comparing how bright these objects appear to how bright they should be, astronomers can calculate how far away they are. By measuring how fast these objects are moving away from us, they can determine the expansion rate. The other approach uses observations of the very distant universe. Specifically, it uses the cosmic microwave background. Scientists measure the pattern of temperature fluctuations in the CMB with extraordinary precision. They then use our best model of cosmology to calculate how the universe should have evolved from that early state to the present day. This model predicts what the expansion rate should be today. The local measurements give a value for the Hubble constant of approximately 73 kilometers per second per megaparsec. This means that for every megaparsec of distance, roughly 3.3 million light-years, the recession velocity of objects increases by 73 kilometers per second. The CMB-based measurements give a value closer to 67 kilometers per second per megaparsec. The difference is about 9%. 9% might not sound like much, but in cosmology, where measurements have become increasingly precise, this is a significant discrepancy. It is well beyond what can be explained by measurement uncertainties. Both groups have error bars on their measurements, ranges of uncertainty, and those error bars do not overlap. Something is genuinely inconsistent. One possible explanation is that one or both measurements are wrong. Perhaps there is some systematic error that has not been accounted for. Perhaps the cosmic distance ladder has a flaw in one of its rungs. Perhaps the assumptions that go into interpreting the CMB data are incorrect. Scientists have searched extensively for such errors. They have refined their techniques. They have used independent methods to cross-check their results. The tension has not gone away. Another possibility is that our cosmological model is incomplete. Perhaps there is some aspect of how the universe expands that we do not fully understand. Perhaps the expansion rate has changed over time in ways our models do not predict. Perhaps there is some new physics, some unknown component of the universe that affects the expansion in ways we have not accounted for. Or perhaps the issue is not with the measurements or the model, but with our location. This is where the supervoid hypothesis becomes relevant. If we are inside a large, underdense region, it could affect the local measurements in ways that make them appear inconsistent with the global average. Here is how it would work. When we measure distances to nearby galaxies using the cosmic distance ladder, we are implicitly assuming that the matter density around us is typical. The way light travels, the way objects move, the gravitational effects we observe all depend on the density of matter in the region. If we are in an underdense region, matter density is lower than average. This affects the local gravitational potential. It changes how space is curved. These changes are subtle but could systematically bias our distance measurements. More importantly, being in a void affects how we perceive the expansion. In an underdense region, there is less matter to gravitationally slow the expansion. Objects at the edges of the void might appear to be receding faster than they would in an average density region. When we measure their velocities and calculate the Hubble constant, we might get a value that is higher than the true cosmic average. Meanwhile, the CMB-based measurement is not affected in the same way. It measures the average properties of the universe on the largest scales. It is sensitive to the overall matter density and expansion history, not to local variations. If the CMB gives us the true cosmic expansion rate, and our local measurements are biased by residing in a void, that would naturally produce a tension between the two values. The magnitude of the effect depends on the size and depth of the void. A typical void would not produce enough of a bias to explain the Hubble tension, but a very large, very underdense void potentially could. If we are in a supervoid of the scale proposed to explain the CMB cold spot, the bias in local measurements could be several percent, perhaps enough to account for at least part of the discrepancy. This is not a complete solution to the Hubble tension. The numbers do not quite work out perfectly. A void large enough to produce the full 9% difference would need to be even more extreme than what is required to explain the cold spot. But it suggests that local underdensity might be part of the story. It might contribute to the tension, even if it is not the entire explanation. This connection between our location and what we measure reveals something profound about the nature of astronomical observation itself. There is a fundamental limitation to astronomy that we can never overcome. We can only observe the universe from here, from this planet, in this solar system, in this galaxy, in this particular location in space. Every measurement we make, every observation we record, every conclusion we draw is filtered through the lens of our cosmic address. In most sciences, this would not be a significant problem. If you want to understand a mountain, you can walk around it. You can view it from different angles. You can drill core samples from multiple locations. If you want to understand an ocean current, you can place sensors at various depths and distances. You can map the flow from many perspectives. But you cannot walk around the universe. You cannot observe it from a different vantage point. This creates a unique challenge when testing the supervoid hypothesis. If we are inside a large, underdense region, how would we know? What would the signs be? And more importantly, how would we distinguish those signs from what we would expect to see in any typical location? The most direct evidence would come from mapping the density of matter around us in 3 dimensions. If we are in a void, we should see that galaxy density decreases as we look in certain directions, reaches a minimum at some distance, and then increases again as our view extends beyond the void. But measuring density at different distances is not straightforward. It requires knowing both the positions and the distances to vast numbers of galaxies. Distance measurement in astronomy is always challenging. For nearby galaxies, we can use techniques like observing certain types of variable stars whose brightness oscillates in predictable ways. For more distant galaxies, we rely on the redshift of their light, the stretching of wavelengths caused by the expansion of space. Redshift tells us how much the universe has expanded since the light was emitted. In a uniformly expanding universe, redshift translates directly to distance. But if we are in a void, this translation becomes complicated. Objects inside the void with us would have peculiar velocities, motions that are not simply due to cosmic expansion. They would be flowing outward, away from the underdense center. When we measure their redshifts, we would be seeing a combination of expansion and this outward flow. This could make objects appear farther away than they actually are, or closer depending on their position relative to us and the void's center. Disentangling these effects requires extremely precise measurements of many galaxies. We need to map not just their positions on the sky, but their 3-dimensional locations in space. We need to measure their velocities with enough accuracy to detect deviations from pure Hubble flow. And we need to do this for galaxies spanning a large enough volume to see the full extent of any potential void. Even if we could perfectly map our local region, we would face an interpretation challenge. Suppose we found that we are indeed in an underdense region. How underdense would it need to be to count as evidence for the supervoid hypothesis? The universe is lumpy. Variations in density are expected. Small voids are common. Even moderately large voids are not shocking. At what point does a local underdensity become so extreme that it demands a special explanation? There is also the question of scale. Our observations are limited by the cosmic horizon, the maximum distance from which light has had time to reach us since the Big Bang. This horizon is currently about 46 billion light-years away, accounting for the expansion of space during light's journey. Everything we can possibly observe lies within this sphere. If we are in a supervoid that spans 1 billion or 2 billion light-years, we are talking about a structure that fills a significant fraction of our observable volume. But it is still just a small part of the entire universe. We have no way to know if other supervoids exist beyond our horizon. We have no way to know if being in such a structure is truly rare on cosmic scales, or if it simply seems rare based on our limited view. This is a fundamental limitation. We can calculate probabilities based on our models of structure formation, but those probabilities assume our models are correct and complete. If there is something about the universe's initial conditions or evolution that makes large voids more common than our models predict, we would have no way to know it from our single vantage point. Another challenge comes from time. Structure in the universe evolves. The distribution of galaxies today is different from what it was 1 billion years ago, and will be different 1 billion years from now. When we look at distant galaxies, we are seeing them as they were in the past. Light from a galaxy 1 billion light-years away left that galaxy 1 billion years ago. We are seeing it as it was then, not as it is now. If we are trying to map the three-dimensional structure around us, we are actually mapping structure at many different times. Nearby galaxies we see as they were recently. Distant galaxies we see as they were long ago. In a young universe, this time difference would matter less. But we live in a mature universe where structure has had billions of years to evolve. The void we see when looking at distant galaxies might have been smaller or shaped differently than it is now. Or perhaps it did not exist yet at all. There is also the possibility of misidentifying local features as global ones. Suppose we find an underdense region in our neighborhood. How do we know this is a supervoid that affects our cosmological measurements rather than just a typical void that happens to surround us by chance? We would need to demonstrate that it is unusually large and unusually empty compared to voids elsewhere. But measuring voids elsewhere requires looking at distant structures where our measurements are less precise. Despite these challenges, astronomers have developed ingenious methods to test whether our cosmic neighborhood is truly unusual. Over the past several decades, astronomers have undertaken massive surveys to map the positions of galaxies across the sky. These are not small projects. They involve pointing telescopes at millions of galaxies, measuring their brightness in different wavelengths, and most importantly, measuring their redshifts to determine their distances. The goal is to create a three-dimensional map of cosmic structure, to see not just where galaxies appear on the sky, but where they are located in the vast volume of space around us. One of the earliest major surveys was the CFA Redshift Survey, conducted in the 1970s and 80s. It mapped roughly 15,000 galaxies. Even this relatively modest number revealed the large-scale structure of the universe for the first time. Galaxies were not randomly distributed. They clustered along filaments and walls. And there were voids, empty regions where few galaxies could be found. Later surveys expanded dramatically. The 2-degree field galaxy redshift survey mapped more than 200,000 galaxies. The Sloan Digital Sky Survey has catalogued millions. More recent efforts like the Dark Energy Survey and the ongoing observations from various observatories continue to push these numbers higher. Each survey reaches deeper into space and maps a larger volume of the universe. When scientists analyze this data, they look for patterns. They measure the distribution of galaxies as a function of distance. They calculate the density of matter in different regions. They identify voids and quantify their properties. And they have found something interesting. We do appear to be in an underdense region. The evidence comes from comparing the local density of galaxies to what we expect based on the cosmic average. When astronomers count galaxies within a few 100 million light-years of us and compare this to the number density they observe at greater distances, they find a deficit. There are fewer galaxies nearby than the cosmic average would predict. This underdensity is not dramatic, but it is measurable. Depending on exactly how you define the boundaries and measure the density, the local region contains perhaps 10 to 30% less matter than average. This structure has been called the KBC void, named after the astronomers who first characterized it in detail. It appears to extend several 100 million light-years in radius, making it one of the largest known voids. Our galaxy sits somewhere within this structure, though not necessarily at its center. The void is not perfectly spherical. Like most cosmic structures, it has an irregular shape, denser in some directions and emptier in others. The existence of the KBC void is not particularly controversial. Most astronomers who have examined the data agree that we are in an underdense region. The question is whether this region is significant enough to affect our cosmological observations. Is it just a typical large void, or is it something more extreme? Some studies suggest that the KBC void, while large, is not exceptionally rare. Voids of this general size and depth do appear in simulations of structure formation with reasonable frequency. If you run many simulations and look at random locations in each one, you might find yourself in a void similar to the KBC void in perhaps 5 or 10% of cases. Not common, but not shocking either. Other studies argue that the void is more unusual than this. They suggest that when you account for its size, its depth, and its relatively smooth structure, it becomes a rarer feature. Perhaps only 1 or 2% of locations would find themselves in such a void. This is still not impossibly rare, but it does push toward the edge of what we would expect by chance. The challenge in settling this question is that we only have one universe to observe. We cannot run the experiment multiple times to see how often voids like ours appear. We can run computer simulations, but those simulations depend on our models being correct. If there is something about structure formation that we do not fully understand, the simulations might not accurately represent the true probability of finding ourselves where we are. There is also ongoing debate about whether the KBC void is large enough to explain the observations that motivated the supervoid hypothesis in the first place. The cold spot in the CMB, if caused by a void, would require something on the order of 1 billion or more light-years across. The KBC void, as currently mapped, appears to be several hundred million light-years in radius, which translates to perhaps 500 to 700 million light-years in diameter. This is large, but not quite large enough to produce the required effect. However, the boundaries of voids are not sharp. They do not have well-defined edges. Density decreases gradually as you move from the denser regions into the void, and it increases gradually as you move out the other side. Where exactly you draw the boundary depends on how you define it. If you use a generous definition, accounting for the gradual transition regions, the effective size of the local underdensity could be larger. There is also the possibility that we are not at the center of the relevant structure. If we are located off to one side of a larger void, our local measurements might not capture its full extent. We might see a moderate underdensity in our immediate neighborhood, while being embedded in a much larger structure whose full scale is only apparent when you look at greater distances. Surveys are ongoing. New telescopes are coming online. The volume of space that has been mapped in detail continues to grow. Each new survey provides more data points, more galaxies, more information about the three-dimensional structure surrounding us. But even with these improvements, fundamental uncertainties remain. We are still observing from a single location. We are still trying to infer global properties from local measurements. The data shows we're in an underdense region, but the question remains, is it just a typical void or something far more extreme? The Copernican principle has been our guide for centuries. It tells us that we should not assume we occupy a special place in the universe, that our location is ordinary, that what we see from here is what anyone, anywhere would see. This principle has served us well. It has kept us from making the mistake our ancestors made when they placed Earth at the center of everything. But the supervoid hypothesis asks us to consider that we might be somewhere unusual after all. Not at the center of the universe, which has no center, but in a location that is statistically rare. This creates an uncomfortable tension. How rare can our location be before it becomes implausible? Consider the numbers. If a supervoid like the one proposed spans roughly 1 billion light-years, it occupies a certain volume of space. That volume is large by our standards, but it represents only a small fraction of the total volume of the observable universe. The observable universe extends more than 40 billion light-years in every direction from us. Its total volume is immense, dominated by regions that are not inside supervoids. If you were to pick a random location in the universe, what would be the probability of landing inside a supervoid? It depends on how common such structures are. If supervoids make up 1% of the universe's volume, then the probability is 1 in 100. If they make up 1/10 of 1%, then 1 in 1,000. The supervoid hypothesis requires us to accept that we happen to be in that rare percent or fraction of a percent of space. This is not impossible. Rare things do happen. If you flip a coin 10 times and get 10 heads in a row, that is unlikely, with odds of roughly 1 in 1,000. But someone somewhere, will experience this. In a universe with potentially many observers, someone will inevitably find themselves in the rare locations. The question is whether we should believe that we are that someone without very strong evidence. There is a counter-argument rooted in anthropic reasoning. Perhaps we need to be in a void for observers like us to exist at all. Perhaps the conditions that allow for the formation of galaxies, stars, planets, and ultimately life are more favorable in underdense regions. This seems counterintuitive, as structure formation is generally more vigorous in dense regions. But maybe there is some aspect of habitability that we do not fully understand that makes voids more conducive to life. This argument is speculative. We have no evidence that life requires underdense environments. Our galaxy formed and evolved without any apparent need for a supervoid. The conditions that led to our existence seem to be common throughout the universe, not restricted to rare locations. Invoking anthropic selection to explain our location feels like reaching for an explanation that is not well motivated by what we know about biology and astrophysics. Another way to think about the probability problem is to ask not whether we are in a rare location, but whether being in such a location would be obvious from our observations. If supervoids affect our measurements in subtle ways, we might not realize we are in one unless we look very carefully. Perhaps many observers throughout the universe are in similar situations without knowing it. Perhaps being in a void is more common than the simple volume calculation suggests, because voids occupy a larger fraction of the universe than we currently believe. This possibility cannot be ruled out. Our understanding of structure formation comes from models and simulations. If those models are missing some ingredient, some process that makes large voids more common than predicted, then the probability problem might be less severe. But this feels like explaining one unknown with another. We would be proposing that our models are wrong in just the right way to make our location less special. There is also the question of selection effects in how we do cosmology. We make observations and develop theories based on what we see. If our location biases what we see in systematic ways, then our theories might be subtly incorrect. They might work well for describing the universe on average, but fail to account for variations that depend on location. This could create a false sense that our observations are typical, when in fact they are shaped by where we happen to be. Disentangling this is extraordinarily difficult. We cannot step outside our location to check. We cannot observe the universe from a neutral vantage point and then compare it to what we see from here. All we can do is try to model what different locations would see and ask whether our observations are consistent with being in a typical location, or whether they require something unusual. The statistical argument against the supervoid hypothesis is not a proof that it is wrong. It is simply a reason for caution. Extraordinary claims require extraordinary evidence. If we are going to accept that we occupy a rare location in the universe, we need very strong reasons to believe it. The cold spot in the CMB and the Hubble tension provide some motivation, but are they strong enough? Some scientists argue yes. They point out that both observations are genuinely puzzling and that the supervoid hypothesis offers a coherent explanation for both. They note that the alternative explanations also have their own challenges and implausibilities. Perhaps accepting that we are in a rare location is no more problematic than accepting that the cold spot is a 1 in 100 statistical fluke, or that there is new physics we have not yet discovered. Others argue no. They emphasize that the probability problem is severe and that we should exhaust all other possibilities before embracing a hypothesis that violates the Copernican principle. They suggest that there are still unexplored alternatives and that the evidence for a supervoid is not yet compelling enough to justify such a radical conclusion. This statistical puzzle forces us to confront an even deeper question about the universe's fundamental nature. The supervoid hypothesis is not the only explanation for the cold spot in the cosmic microwave background. Scientists have proposed several alternatives, each with its own merits and challenges. Understanding these competing ideas helps clarify what makes the supervoid hypothesis attractive and where it might fall short. The simplest explanation is that the cold spot is exactly what it appears to be at first glance: a rare but perfectly normal temperature fluctuation from the early universe. The initial density variations that seeded all cosmic structure were fundamentally random. They arose from quantum fluctuations during inflation, stretched to cosmic scales. Random processes produce a range of outcomes. Most fluctuations are small, but occasionally, purely by chance, a larger fluctuation occurs. If you create many simulations of the early universe, each with different random initial conditions, you will sometimes see features like the cold spot. Not often, but sometimes. Perhaps 1 in 50 simulations. Perhaps 1 in 200, depending on exactly how you measure the cold spot's properties. The question is whether we should accept that we simply happen to live in the universe that got the rare fluctuation. This explanation requires no new physics. It invokes no unusual structures. It simply says that unlikely things sometimes happen. In a sense, it is the most conservative explanation, but it is also somewhat unsatisfying. It essentially says the cold spot is just bad luck, or good luck, depending on your perspective. It teaches us nothing beyond confirming that random processes do indeed produce rare outcomes. Another possibility involves topological defects. These are hypothetical structures that could have formed during phase transitions in the very early universe, similar to cracks that form in ice as water freezes. Different types of defects have been proposed over the years: cosmic strings, domain walls, monopoles, textures. Most of these have been ruled out by observations or are predicted to be extremely rare. But some models suggest that certain types of textures could produce temperature variations in the CMB that resemble the cold spot. A texture is a knot in the fabric of space itself, a region where certain quantum fields are twisted in a particular way. As the universe expands, a texture can unwind, releasing energy in the process. This could create a hot or cold spot in the CMB, depending on the details. The texture explanation has the advantage of being more predictive than a random fluctuation. It makes specific claims about the properties the cold spot should have. But it also requires accepting that these exotic objects exist, and that we happen to be looking at one in just the right way. There are also modified gravity theories. Our understanding of cosmology is built on Einstein's general relativity, which describes how matter and energy curve space, and how that curvature affects motion and light. General relativity has passed every test we have thrown at it, from the orbit of Mercury to the detection of gravitational waves. But perhaps On the largest cosmic scales, gravity behaves slightly differently than Einstein predicted. Various modified gravity theories have been proposed to explain phenomena like dark energy and the accelerating expansion of the universe. Some of these theories predict slightly different patterns in the CMB than standard general relativity. It is conceivable that the cold spot could be a signature of modified gravity, evidence that our theory of space-time needs revision. This would be a profound discovery, but the bar for overturning general relativity is very high. We would need extensive evidence that cannot be explained within the standard framework. Then there is the multiverse perspective. Some interpretations of quantum mechanics and some versions of inflation theory suggest that our universe is just one of many, perhaps infinitely many, universes that exist in a larger multiverse. Each universe in this ensemble might have different properties, different physical constants, perhaps even different laws of physics. In this framework, the cold spot might not need an explanation at all, at least not in the traditional sense. If there are countless universes with all possible configurations of initial conditions, then somewhere there will be universes with cold spots like ours. We observe the particular universe not because it is typical, but because it is the one we happen to inhabit. This is an extreme form of anthropic reasoning. It does not explain why the cold spot exists, but rather why we should not be surprised to see it. The multiverse explanation is philosophically challenging. It is difficult to test. If other universes exist but are causally disconnected from ours, we cannot observe them directly. We can only make inferences based on whether our universe's properties seem fine-tuned or improbable in ways that might suggest a multiverse. Many scientists are uncomfortable with explanations that cannot be tested empirically. What all of these alternatives have in common is that they attempt to explain the same observation without requiring us to be in a special location. They preserve the Copernican principle by attributing the cold spot to either random chance, exotic physics, modified gravity, or the anthropic properties of a multiverse. In each case, the cold spot is not about where we are. It is about what happened in the early universe, or about the fundamental laws of nature. The supervoid hypothesis is different. It makes the cold spot about where we are right now. It connects an observation of the ancient universe to the structure that surrounds us today. In that sense, it is more testable than some alternatives. If we are in a supervoid, we should be able to measure it through galaxy surveys and other local observations. We do not need to invoke exotic early universe physics or modify our fundamental theories. We simply need to accept that our location might not be typical. But acceptance comes at a cost. It means setting aside a principle that has guided cosmology for centuries. It means believing that we are among the small fraction of observers who happen to live in a rare part of the universe. Each alternative hypothesis carries its own implications, but they all share something in common. They are forcing us to question our cosmic models. If the supervoid hypothesis is correct, if we truly reside within an enormous underdense region of space, the implications ripple through nearly every aspect of cosmology. It would not overturn physics. The fundamental laws that govern matter, energy, space, and time would remain unchanged. But it would mean that many of our measurements, many of the numbers we use to describe the universe, might need to be reconsidered. Start with the expansion rate. As we have discussed, Being in a void could bias local measurements of the Hubble constant. If our measurements are systematically too high because we are in an underdense region, then the true cosmic expansion rate might be lower than what we have been reporting. This would affect our understanding of dark energy, the mysterious component that drives the accelerated expansion of the universe. Dark energy is inferred primarily from observations of distant supernovae. These exploding stars serve as standard candles, objects whose intrinsic brightness is known. By measuring how bright they appear and comparing that to how bright they should be, we can determine their distances. By measuring their redshifts, we can determine how fast they are receding from us. When astronomers first did this systematically in the late 1990s, they discovered something unexpected. Distant supernovae were dimmer than predicted. This meant they were farther away than expected for their redshift. The only way to explain this in standard cosmology was to invoke an accelerating expansion driven by dark energy. But if we are in a void, this analysis becomes more complicated. Light traveling through underdense regions experiences less gravitational attraction than light traveling through average density regions. This could make distant objects appear slightly dimmer, slightly farther away than they would in a uniform universe. The effect would be subtle, but if not accounted for, it could lead us to overestimate the strength of dark energy. The amount of this bias depends on the size and depth of the void, and on where we are located within it. If we are near the center of a large void, light traveling in all directions passes through similar underdense regions, and the effect might partially cancel out. If we are off-center, light traveling in different directions experiences different density profiles, and the effect becomes more complex. Calculating these effects requires detailed modeling and depends on assumptions about the void structure. Some studies suggest that a void of the scale we have been discussing could account for a portion of the inferred dark energy. Perhaps dark energy is not as strong as we think, or perhaps it does not exist at all, and what we attribute to it is actually the effect of our location. Other studies argue that the void would need to be even more extreme than what is plausible to fully eliminate the need for dark energy. The consensus is that dark energy is real, but its precise strength might be affected by local underdensity. There are also implications for our understanding of the universe's expansion history. Cosmologists reconstruct how the expansion rate has changed over time by observing objects at different distances and therefore different epochs. Nearby objects show us the recent past. Distant objects show us the ancient past. By piecing together observations across this range, we build a picture of how the universe has evolved. If our local measurements are biased by a void, then our reconstruction of the recent expansion history might be incorrect. We might think the universe has been accelerating at a certain rate for the past few billion years, when in fact the acceleration has been different. This would affect our models of dark energy evolution. It would change predictions for the universe's future. It might even alter our estimates of the universe's age, though probably not by much, given the constraints from other observations like the cosmic microwave background. Distance measurements would also be affected. Astronomers use various methods to measure distances to galaxies and other objects. Many of these methods rely on assumptions about how light travels through space and how the universe expands. If those assumptions are based on us being in a typical location, and we are not, then the distances we calculate might be systematically wrong for certain objects. This does not mean all of astronomy would be upended. Distances to nearby objects would be largely unaffected, but distances to objects at intermediate ranges, within a few billion light-years, could have systematic errors. This would affect estimates of galaxy sizes, luminosities, and masses. It would influence studies of galaxy evolution and star formation history. It would introduce uncertainties into measurements of large-scale structure. Cosmological parameters, the numbers that describe the composition and properties of the universe, would also need revision. Right now, we say the universe is roughly 68% dark energy, 27% dark matter, and 5% ordinary matter. These percentages come from combining many different observations and finding the model that best fits all of them. If some of those observations are biased by our location, the best fit model might change. The changes would likely be small. We are not talking about discovering that the universe is 90% dark energy or 50% ordinary matter. The broad picture would remain the same, but the precise values which cosmologists have worked hard to measure with percent-level accuracy might shift by a few percentage points. This matters for testing detailed theoretical predictions and for understanding the universe's ultimate fate. It is worth emphasizing again that none of this would represent a failure of physics. General relativity would still be correct. The laws of thermodynamics, quantum mechanics, electromagnetism, all would remain unchanged. What would change is our understanding of where we are within the structure predicted by those laws. It is the difference between thinking you are measuring the temperature of a room from its center and discovering you have been standing next to an open window. The thermometer still works. The laws of thermodynamics still hold. But your measurement is not representative of the room as a whole. Beyond the technical implications for cosmology, this hypothesis touches something more fundamental about how we understand our place. There is something deeply human about wanting to know where we are. Not just in the practical sense of navigation, but in the cosmic sense. Where do we stand in the vast architecture of existence? Are we at the center, on the edge, somewhere in between? Throughout history, our answer to this question has evolved, and each evolution has changed how we see ourselves. For most of human history, we believed we were at the center of everything. Earth was the unmoving foundation upon which the heavens turned. The sun, the moon, the planets, the stars, all revolved around us. This was not merely observational astronomy. It was philosophy and theology intertwined. Being at the center meant something. It implied significance, purpose, a special relationship between humanity and the cosmos. Nicholas Copernicus challenged this view in the 16th century. He demonstrated that a simpler, more elegant model emerged if you placed the sun at the center and allowed Earth to orbit along with the other planets. This was not easy to accept. It displaced us from the center. It suggested we were not special after all, at least not in terms of our cosmic address. The Copernican revolution was not just about planetary motion. It was about relinquishing a claim to centrality. Over the following centuries, we discovered just how far we had been displaced. Our sun was not the center of the universe. It was one star among countless others in a galaxy. Our galaxy was not the center. It was one galaxy among countless others in an expanding universe. Each discovery reinforced the same message. We are not central. We are not in a privileged location. Our cosmic address is ordinary. Edwin Hubble's discovery of the expanding universe in the early 20th century cemented this view. If every galaxy is moving away from every other galaxy, then no location is special. There is no center to the expansion. An observer in any galaxy would see the same pattern of expansion, would measure the same cosmic properties. This became the foundation of modern cosmology. The universe looks the same from everywhere, and therefore our observations from here are representative of the universe as a whole. The supervoid hypothesis asks us to reconsider this. It suggests that perhaps we are somewhere unusual after all. Not at the center of the universe, which remains a meaningless concept in modern cosmology, but in a location that is statistically rare, a region of lower than average density, a cosmic bubble that affects what we see when we look outward. There is irony in this. After centuries of learning that we are not special, we are confronted with the possibility that our location might be special in a different way. Not because the universe was designed with us at its center, but because structure formation is a stochastic process that produces variations, and we happen to be in one of the less common variations. But is special even the right word? In an infinite universe, or even in a finite but very large universe, every type of location exists somewhere. There are observers in dense clusters surrounded by thousands of galaxies. There are observers in typical regions threaded by filaments. There are observers in small voids, large voids, and perhaps even supervoids. If all of these locations exist, none of them is truly special. They are just different. From this perspective, the question is not whether our location is special, but whether it is typical. And typical is a statistical concept. It depends on what fraction of the universe or what fraction of potential observers occupies each type of location. If most observers are in average density regions, then being in a supervoid would be atypical. But if voids are common enough that a significant fraction of observers reside in them, then being in a void might be more typical than it first appears. There is also the matter of observer selection. We can only observe the universe from locations where observers can exist. If there is something about our type of life, or our type of planet, or our type of galaxy that makes it more likely to form in certain environments, then those environments would be overrepresented among actual observers. This does not mean the environments are typical of the universe as a whole, only that they are typical of places where observers happen to be. This line of thinking becomes speculative quickly. We do not know enough about the requirements for life or the likelihood of life emerging in different environments to draw firm conclusions. But it reminds us that typical for the universe and typical for observers might be different things. There is a deeper philosophical question embedded in all of this. Does it matter where we are? If the laws of physics are the same everywhere, if the fundamental nature of reality is unchanged regardless of location, does our cosmic address have any real significance? In one sense, no. The equations that govern atoms, light, gravity, and quantum mechanics do not care whether we are in a void or a cluster. A physicist in a galaxy within a dense supercluster would discover the same laws we have discovered, But in another sense, yes, it matters enormously. Our observations are shaped by our location. What we see, what we measure, what puzzles we encounter, all depend on where we happen to be. If we are in an unusual location, then our observations might not be representative. The cosmology we have built might be correct for our local region, but incomplete as a description of the universe as a whole. This realization does not diminish the achievement of science. It does not mean our theories are wrong. It means that science is hard and that doing cosmology from a single vantage point requires extraordinary care. It means we must always be aware of the assumptions we make and the ways our perspective might bias our conclusions. As we grapple with these questions about where we are, we also have to consider what future observations might finally settle the matter. Science does not stand still. While we grapple with the supervoid hypothesis and what it might mean, new telescopes are being built, new surveys are being planned, and new methods are being developed. The next decade promises to bring a wealth of data that could help resolve this mystery, or at least narrow the range of possibilities. One of the most ambitious projects currently underway is the Euclid Space Telescope, launched by the European Space Agency. Euclid is designed to map the geometry of the universe by observing billions of galaxies across more than a third of the sky. It will measure their positions, their shapes, and their distances with unprecedented precision. The goal is to understand dark energy and dark matter, but the data will also be invaluable for mapping large-scale structure. With Euclid's observations, astronomers will be able to create a three-dimensional map of the universe, extending billions of light-years in every direction. This map will reveal the distribution of matter on the largest scales. It will show where voids are located, how large they are, and how empty they are. If we are in a supervoid, Euclid should be able to characterize it in far greater detail than current surveys allow. On the ground, the Vera Rubin Observatory is preparing to begin its legacy survey of space and time. This telescope, located in Chile, will repeatedly scan the entire visible sky every few nights for at least 10 years. It will catalogue billions of galaxies and measure changes in the sky over time. While its primary goals involve studying dark energy, dark matter, and transient events like supernovae, it will also provide an enormous dataset for studying cosmic structure. The combination of Euclid's space-based observations and Vera Rubin's ground-based survey will give astronomers an unprecedented view of the universe's architecture. They will be able to measure the properties of voids with far greater statistical power than is currently possible. They will be able to compare the structure around us to the structure in distant regions and determine whether our local environment is genuinely unusual. Improvements in measuring the cosmic microwave background will also help. While the basic map of the CMB is already very detailed, there are still refinements to be made. Future experiments will measure the polarization of the CMB with greater precision. Polarization carries information about how light scattered in the early universe and about the gravitational waves that may have been produced during inflation. It also provides an independent way to check for anomalies like the cold spot. If the cold spot is caused by a supervoid through the integrated Sachs-Wolf effect, it should have a particular polarization signature. The pattern of polarization around the cold spot should differ from what you would expect if the cold spot were simply a primordial fluctuation from the early universe. Future measurements may be able to distinguish between these scenarios, providing a crucial test of the supervoid hypothesis. There is also a relatively new tool in the astronomer's toolkit: gravitational waves. When massive objects like black holes or neutron stars orbit each other and merge, they create ripples in space-time that propagate outward at the speed of light. These ripples were first detected in 2015, confirming a prediction of general relativity and opening an entirely new way to observe the universe. Gravitational wave observations are still in their infancy, but they hold promise for cosmology. When a gravitational wave from a merger is detected, the waveform tells us about the masses of the merging objects and the strength of the wave. If we can also identify the galaxy where the merger occurred and measure its redshift, we can use this information to determine the distance to the merger. This provides an independent way to measure cosmic expansion that does not rely on the traditional distance ladder. As the network of gravitational wave detectors improves and more mergers are detected, astronomers will be able to build up a catalogue of these measurements. If we are in a void, it might affect the pattern of these measurements in detectable ways. The distances inferred from gravitational waves might systematically differ from distances inferred by other methods for objects in certain directions or at certain ranges. This would provide yet another test of whether our local environment is unusual. Of course, there is no guarantee that these future observations will provide a definitive answer. Science rarely works that way. More likely, the new data will refine our understanding, narrow the range of possibilities, and perhaps raise new questions we have not yet considered. Each observation will need to be interpreted carefully, with attention to potential biases and systematic errors. There is also the possibility that the answer will remain ambiguous. Even with the best data, we might find that multiple explanations fit the observations reasonably well. The universe might not cooperate by providing clear, unambiguous evidence for one hypothesis over another. We might have to learn to live with uncertainty, to accept that some questions do not have clean answers given the observational constraints we face. The timeline for these observations spans roughly the next decade. Euclid and Vera Rubin will collect data over many years. Gravitational wave detectors will gradually build up their catalogues of events. CMB experiments will continue to refine their measurements. By the early 2030s, we should have a much clearer picture of our cosmic neighborhood and whether it is truly unusual. But even if we never achieve absolute certainty, even if the supervoid hypothesis remains one possibility among several, the question itself has already proven valuable. It has forced cosmologists to think carefully about their assumptions. It has highlighted the importance of understanding local structure when making global inferences. It has reminded us that doing science from a single vantage point is inherently challenging and requires constant vigilance against biases. Whether we ever know for certain or not, the question itself has already changed how we think about cosmic structure. There is a particular kind of beauty in not knowing, in having a question that resists easy answers, in standing at the edge of understanding and recognizing that the edge is where the most interesting things happen. The supervoid hypothesis, whether ultimately confirmed or refuted, represents this kind of question. It asks something fundamental about our place in the cosmos and offers no simple resolution. We have built a remarkable picture of the universe over the past century. We know it is expanding. We know it began in a hot, dense state nearly 14 billion years ago. We know it is filled with galaxies, clusters, filaments, and voids arranged in a vast cosmic web. We know the basic laws that govern how matter and energy behave across enormous scales of space and time. This is an extraordinary achievement, one that required countless observations, brilliant insights, and painstaking work by generations of scientists. Yet within this picture, there are puzzles. The cold spot in the cosmic microwave background that should not be as large or as cold as it is. The tension between different measurements of the expansion rate. The question of whether our local environment is representative of the universe as a whole. These are not failures of science. They are invitations to look deeper, to question our assumptions, to consider possibilities we might have dismissed too quickly. The idea that we might reside inside an enormous cosmic void is unsettling precisely because it challenges the Copernican principle that has guided us for so long. We have grown comfortable with the notion that our location is ordinary, that what we see from here is what anyone, anywhere, would see. To entertain the possibility that we are somewhere unusual requires us to hold two thoughts simultaneously. On one hand, we should not assume we are special without strong evidence. On the other hand, we should not cling to the assumption of typicality if the evidence points elsewhere. This is the heart of good science, being willing to follow the evidence wherever it leads, even if it takes us to uncomfortable places, being skeptical of extraordinary claims while remaining open to the possibility that the universe is stranger than we thought. Balancing caution with curiosity. If future observations confirm that we are in a supervoid of the scale proposed, it will require a shift in how we think about cosmology. Not a revolution that overturns physics, but a recalibration of our understanding. We would need to account for our location when interpreting observations. We would need to be more careful about extrapolating from local measurements to global conclusions. We would need to revisit some of our most cherished numbers and ask whether they represent cosmic averages or local peculiarities. But even this would not diminish what we have learned. It would simply add nuance to our understanding. It would remind us that the universe is large and complex, and that doing science from a single vantage point requires humility and care. The laws of physics would remain unchanged. The expansion of the universe would still be real. Dark energy and dark matter would still exist. We would simply have a better understanding of how these things manifest in different environments. If, on the other hand, future observations show that we are not in an unusual location, that the cold spot and the Hubble tension have other explanations that would also be valuable. It would vindicate the Copernican principle and reassure us that our observations are indeed representative. It would point us toward different solutions to the puzzles that motivated the supervoid hypothesis. Perhaps exotic physics from the early universe. Perhaps modifications to general relativity. Perhaps subtleties in how we measure distances or interpret data. Either outcome would advance our understanding. This is what makes the question worth asking, regardless of the answer. It is not really about whether we are in a void. It is about learning to ask the right questions, developing the tools to answer them, and being honest about the limits of what we can know from where we are. There is something profound in the act of a species that evolved on a small, rocky planet, orbiting an unremarkable star in one galaxy among hundreds of billions, looking outward and asking, "Where are we?" Not just in the sense of navigation, but in the deeper sense of understanding our relationship to the cosmos. Asking whether the view from here is typical or unusual. Wondering whether the universe looks the same from everywhere or whether our perspective is shaped by our particular location in ways we have not fully appreciated. This question connects to something ancient in human nature. We have always wanted to know where we stand, to understand our context, to map our surroundings. The tools have changed dramatically. We now use telescopes that detect light from billions of years in the past. We analyze data from millions of galaxies. We run simulations on supercomputers. But the fundamental impulse remains the same. We want to know where we are. Perhaps we will never have a definitive answer. Perhaps the universe is too large, too complex, too filled with structure on multiple scales for us to ever be certain that our location is typical or atypical. Perhaps the question itself will evolve as we gather more data and refine our models. New puzzles will emerge. New hypotheses will be proposed. The boundary of the known will shift, but it will always remain a boundary. And that is all right. That is in fact how it should be. Science is not about achieving perfect certainty. It is about progressively refining our understanding, acknowledging uncertainty while still making progress, learning to ask better questions even as we answer old ones. We are here wherever here is, looking outward. The universe stretches around us in all directions, filled with structure and mystery. We measure what we can measure. We theorize about what we cannot. We build models and test them against observation. We argue about interpretations and refine our techniques. This is the work of understanding. It is slow and painstaking and beautiful. Asking where we are is itself a profound expression of consciousness in the cosmos, regardless of the answer.